All right, so let's go ahead and get started. So in this lecture, we're going to be talking about high swing current sources, which is sort of a continuation of what we were talking about last time. Last time we were talking about swing, and we'll finish that up and then start into these current sources. Just reminders, which are really announcements from last time. The Monday labs, you won't have them. They're shifted to the week after. And the lab number ones are due on Tuesday next week for the Monday section per Travis's email. And I think that's it in terms of announcements. I'm going to wait till everyone in the class has shown up before I pass out these things up here, which are your graded homework number 1 and 2s coming back to you. I think that's all the logistics I have to take care of, right? Okay. Yeah.
So when you define swing, output swing, is it defined as the point when one of the peaks or troughs starts clipping, or is it when both start?
It's when both start clipping. So the top and bottom side is what it is. You want to know what that. You want to know what the largest sinusoid you can put on this thing. You'd like to know what it is. But I guess it's both clipping if you're biased exactly in the center between those two. But if you're biased somewhere down here, I guess arguably you could still say, when you're doing things like calculating dynamic range or so, you're going to assume your bias point is in the best point that it can be in. Does that make sense what I'm saying? Okay. So you'll always really define the output swing as if your bias point is exactly in the right place when you're doing a dynamic range calculation. But if you're not doing dynamic range calculation, say your bias point is lower than where it should be, then the swing really becomes where it first clips, whether it's top or bottom. Okay? I'm going to draw some pictures of that in a second to make that clearer then. There was another question. Did you have a question? There's a similar question? Okay. Yeah, let me talk more about that as we get into this lecture. And so, we'll continue output swing, then high swing current sources. So we're going to design current sources specifically so we can get maximum swing. And mainly we're going to be worrying about cascode type current sources. Okay, and then we'll talk about current source matching considerations, which I anticipate we won't be able to get to at this lecture, but that's coming probably the next lecture. And so just a bit of review from last time. We were sort of defining output swing right here. And this is not the best picture in the world, because in this picture, I'm sort of just thinking about the bottom part here, and I sort of said that don't worry about the top part just to simplify this, okay, which is not a correct picture here. This is only the picture that you have if this V out, V naught here, is closer to ground than to VDD. Okay, so I'll draw this picture again when we're finished with this. Well, we already finished this, so I'm going to draw this picture again in a second. All right, but this is what we did last time because I wanted to show this is what it looks like when it's linear. This is what it looks like when it's nonlinear at the bottom. Okay, we went through the analysis here and we thought about the transfer characteristic for a transistor, the ID versus VDS curves, and we recalled that these curves were nonlinear. And so usually we're operating in this region here where the transistor is saturated. But if your output makes too large an excursion, say downward in this case for this circuit, then your VDS for M1 becomes too small. Right? The VDS becomes smaller than what's called the VDSat, or the overdrive voltage, which is sort of the minimum voltage that VDS has to be in order to keep that transistor saturated. So if that voltage, say if V naught here falls below an overage voltage, VOV, across M1, then M1 is going to go from this region, which is saturation, to this region, where you see the smaller VDSs here. And so suddenly its slope is going to change. Okay? And so in both of these regions, you could sort of say the slope is linear, right? That's sort of a linear slope, but it's a very small slope, which means the output resistance is very large. This is also a linear slope, but it's a much larger slope, and on this current versus voltage plot, that means the output resistance of the transistor is very small. Okay, so in any of these regions, you can define an output resistance for the transistor. Just in this region, I'll call it R naught prime. R naught prime is going to be much smaller than R naught. Okay? And so that's why we're worried about if this transistor goes from saturation to the triode region. Okay? Because once it goes from saturation to the triode region, that gain changes. And as soon as the gain changes, your waveform goes from something that's nice and smooth to something that suddenly flattens out there. Okay? And that's how when you start increasing this waveform, you end up with a square wave on a lot of these transistor circuits. Okay? Any questions about that? About what we're worried about here? We're mainly worried about keeping all transistors saturated. As soon as one transistor goes away from saturated in this circuit, then we're going to have a nonlinearity. And that's how we're defining our swing. Okay? And so I'll say that's how we're defining our swing, because when you get to more advanced courses like 142 or 242, which are courses on nonlinear circuits, there's actually a much more quantitative and accurate mathematics that you can use to determine what it is, what your maximum signal is. It's not just going from saturation to linear. That's our approximation. It has more to do with tonal harmonic distortion and things like intercept points, which you don't know anything about right now and which I'm not going to bother you with right now. This gets pretty close to what those will determine, but those are much more accurate. So when you're buying, for example, headphones, you look at your headphones and they always have some spec on it. There's a total harmonic distortion on it. Right? What that is telling you how nonlinear those headphones are. That if you try to drive them at a certain volume, you'll start hearing some distortion. And of course, you don't like that. Right? And so 142 will teach you how to calculate that. And usually when we define the largest signal that you can put into these circuits, it's going to be the signal that gives you a total harmonic distortion of whatever it is the specification you have, 10% or something. In comms, it's going to be what the intercept point is, the intermodulation intercept point. But these are all terms that you will not learn in this class because it's out of the scope of the class. 142 or 242, take those to learn about that. But for here, our swing is simply going from saturation to triode. Okay, that's the maximum, that's the minimum voltage we can get to, that's the maximum voltage we can get to. Okay? And I pretty much define this overdrive voltage here, which is just VGS minus VT. So that's how much higher your gate to source voltage is than the threshold voltage, and so no wonder we call it the overdrive voltage, because to turn on the transistor you only need to get VGS equal to VT, the threshold voltage, but here usually we're raising it versus VT. And so in this case, VGS VT, which equals our overdrive voltage, equals just rearranging the current equation for the transistor to the square root of the quantity 2 times ID divided by mu n C aux divided by W over L. Okay? And so what this tells you is that you can design what the overdrive voltage is. Right? You can see here are all your design parameters. If you want the overdrive voltage to be large, you make the current very large. You use small W over L ratios. You use bad transistors. Okay? Meaning your mu n C aux is very low. Okay? And so usually, right, you probably want your V overdrive to be very low. Right? And so to do that, you want lower currents, you want larger transistors and better transistors to do that. And we'll talk about why you want that V overdrive to be very low. Well, we already talked about that. And so in this case, I'll also write this equation. Just remember, right, V overdrive is VGS minus VT, but an equally important and useful thing to remember is that VGS equals VT plus V overdrive. Okay, for a saturated transistor, it's VT plus V overdrive. That's going to be very useful very soon for us. And so why is it we want to make V overdrive as small as possible? Because when we look at that circuit that we've been playing with, and I guess what I'll do is just copy this over and redraw that output spectrum there. I'm looking for my little arrows, which I don't seem to have. All right, fine. Try to position this myself. All right, anyway, this is the circuit we were looking at here. And so I want to sort of redraw these curves here and put this sort in perspective where the output DC bias is biased the way that it should be. So let me do this. Make that a little higher there. So that's still my V0 voltage. Right, this is 0 volts down here. That's ground. And then I'll just put symmetrically above this VDD right here. Okay, and so in our calculations from yesterday, if we're looking at this device right here, let's get rid of the clutter here. So if we're looking at this output device, then the lowest that this voltage can get is going to be equal to an overdrive voltage, right? Because if it gets below that overdrive voltage, then M1 goes into the triode region and we get nonlinearity. Okay, so this point right here the lowest we can get before it goes nonlinear is going to be V overdrive. Okay? If we put more gain into this sinusoid here so that it wants to try to get below that point, it's not going to get far below that point because the gain is suddenly going to go away once it passes that point, and it's going to turn into more like a square wave. At the same time, at the top side, I could do exactly the same thing. So here's sort of VDD at the top side. But let's take a look at this. As this output voltage keeps rising here, when is this PMOS transistor, which is our drive transistor, when's that going to go into the triode region? Well, it's the same thing. Once you've dropped, sorry, let me use the right color. Once you've dropped across this a V overdrive, okay, then that transistor also is going to go into the triode region, which means you no longer have maximum gain, you have much smaller gain, and this thing is not going to amplify much. So I could put another point right here and define that as the maximum voltage that the maximum voltage that the output could take without this going into significant linearity. And so this voltage point right here is VDD minus a V overdrive. Okay? And so this is what the real picture should look like without my approximations from yesterday, without me trying to simplify things. This is what it looks like in the end. And so what I'm showing right here is sort of the maximum linear signal that I can apply. Because it's right up against the V out max. And so let me name these things. We'll call this V out max. And this then is going to be V out min. Okay? When you go beyond those, this thing will go nonlinear. And so I'll just draw it. So this, if I've drawn this the way that it is now, let me extend that out, then this sinusoid that I've drawn here is approximately the maximum amplitude sinusoid that keeps everything linear. I should say output sinusoid. That keeps everything linear. And if I go higher than this, so for example, my input becomes an even larger sinusoid. I guess I should draw the input here too to be complete. So my input, which is this voltage here, is going to look something like this versus time. So there's VI, and it'll be first a small sinusoid like this coming in that's amplified. And then if I apply a larger input like this, trying to keep them in phase, but say I put a larger sinusoidal input on this, now that's going to make the output try to go even bigger than what we're seeing right here. All right? And so if it tries to go bigger, what happens? It's got a faster slope going up, but once it hits that, it's got no more gain anymore. Suddenly R naught turns into R naught prime, which is the very small resistance of a triode type transistor. And so instead of continuing to go with a fast slope, this curves out like this. And then it does this, that curves out, And so you get close to a square wave, and eventually if you put a large enough input signal, you'll get a square wave out of this thing. Okay? And so we want to avoid the red. In analog circuits, in most analog circuits, you want to avoid this nonlinearity. Okay, yes?
Is it the beginning of a clock generator in a digital circuit?
Yeah, you can think of this. This is pretty much like a digital circuit in the end. See, digital loves the nonlinearity because the nonlinearity allows you to just define a 1 and a 0. And it turns out that that's much more, it can withstand noise much better than an analog circuit can. Okay, but the problem with this, and if everyone had their way, they would do everything digital. And you can see more and more of that happening, right? Music is recorded digitally. Everything is becoming digital. Even your cell phone, if they could, they would try to make all of it digital. The problem is you can't do that because you and I live in an analog world, right? So the problem is the world is analog, unless you go into quantum physics and that's maybe it's not completely analog. But at least from our viewpoint, the world is analog. And so you have to convert that analog signal to digital first. So that's why analog circuits will always be around, because you have to do that conversion, analog to digital. And oftentimes that's what decides whether you can really process something digitally or not. It's that A to D converter. And so once you learn about A to D converters, which you won't really learn until you take graduate courses or so out here, or wherever you go to grad school, or wherever you go to work, right? Eventually you'll learn about them. And they're all analog circuits. And so and they use op amps, right? So they're mainly op amp type circuits. And so there's where you end up having to really understand op amps well for analog design so that you can do A to D conversion. So you do the A to D conversion, then everything is done digitally after that. Okay? And your cell phones are mainly analog devices because it's much more difficult to convert that EM wave that hits your antenna, amplify that up, then convert that with an A to D converter to digital, then digital is done after that. Okay? So that's what we're worried about. We're worried about being able to handle these analog signals, but why are we worried about the swing? We're worried about the swing because of what's called dynamic range. Okay, so if I look at this, I can define one more thing associated with this plot here, and that is noise. Okay, so this may be my input signal here. So say this is my input signal. But you know that even if I make my input signal 0, okay, so say I draw in my 0 input signal, that's the green. Well, that's supposed to be 0. Let's try to make it a better 0. Okay, so the green equals 0 volts. So even if I put 0 volts into this amplifier, do I get 0 volts out? Pretty much if you just look at it on an oscilloscope. Okay, but usually a lot of these analog circuits have to detect things you can't even see on the oscilloscope unless you really make the volts per division very small. Right? If you zoom in on the signal on an oscilloscope, you never see just a nice flat line coming out. You always see this. Some fuzzy signal there, and that's noise. Okay, that noise comes from your transistor. It can come from feed through from digital circuits that are on the same chip as your analog circuits. Wherever it comes from, it's there. It's a random signal. So pretty much random. And if your output signal after amplification is smaller than that noise, you're not going to see it. Okay, so there's where you're worried about that noise. And so it turns out it's difficult to design a circuit that can both pull something out of this noise. So say we had an output way down in this noise and be able to amplify to very large signals. Okay, so that's why we define what's called the dynamic range. Okay, so the dynamic range ends up being sort of the maximum output signal you have divided by the maximum output noise that you would get with a zero input into this. Because the maximum output noise is the minimum signal you can get. And so this is one thing that analog designers care about a lot. And you'll hear it again and again. Dynamic range, often DR. This is sort of your maximum output signal divided by your maximum input signal. And your maximum input signal, I just mentioned here, this is determined by noise. Your maximum output signal that's determined by exactly what we're talking about. Whoops. It's determined by the output swing. That's why we care about output swing. Okay, so we care about this a lot. In dynamic range, we care about that because we want to maximize this. And in fact, when you buy things, right, headphones and stuff, you're usually looking for the ones with the highest dynamic range. 2 questions I see. Let's go with yours first. Oh, I'm sorry, the minimum input signal. Yeah. What am I doing here? Yeah, thanks. Was that your question too? Yeah. All right, so we care about this dynamic range a lot. Minimum input signal determined by noise, that's another class. At least in this class, we'll take a little bit, we've taken a look at this output swing, okay, and we found that it's determined by that overdrive voltage, at least for this very simple circuit here. Okay, so let's go a little more complicated here. So what about those more complicated circuits that say use a better current source? So what about a circuit using a better current source like a cascode current source? So do you remember the advantages of a cascode current source? Who remembers the advantage of that? So here's a cascode circuit. We're essentially talking about this. We'll stick with a PMOS type drive here, since we started out with that. And this is what it would look like if we made it into a cascode circuit. So this will be our input here. That's VDD. This is our output there. Let's call that M1, M2, M3, and M4. So M4 is sort of our input device. And all these other devices are kind of biasing devices, right? Except for this M3. M3, if you remember, is basically a source to drain type gain, right? So a common gate type device here. But all of these things, you're going to have to determine their V biases. So you have to put in V bias generators at each of the gates of those transistors. And so that's what current source design is all about, right? And so our big question is, how do we generate these? So how do I generate V bias 3? And we're also interested in how we can generate both of these down here. Because that's what the real problem becomes in designing this whole thing. All right, once you've determined using your small signal analysis what the gain is of this thing and the frequency response or something, you're assuming it's biased up in some way. You're assuming it has some drain current, which is what you need to determine GM and R naught and all the other things, right? And so how do we generate these voltages here? And what do we want these voltages to be? Okay? So what do you want these voltages to be? You want them to be such that they will support an output from this that is the maximum swing. All right? So let's talk now about what the maximum swing of this circuit might be. Let me draw another diagram here to show that maximum swing. So we're looking at this function of time, and this is also V naught here, our output voltage. And VDD is right here. Ground is right there. And so in order to get my maximum swing, I want to bias my V naught, which I'll call V naught with that slash through the naught to indicate it's a capital V, capital naught. Okay, the DC bias point, I want to put that right in the center of this, right? Because if I put that right in the center of this, then that allows my swing to be maximum here without going nonlinear. And the reason for that is if I look down this way, the lowest this voltage can go is the sum of one overdrive voltage for device 1 and another overdrive voltage for device 2. Okay? And so because of that, I could say that V out min for this device is going to be 2 times an overdrive voltage. Right? And that would be the maximum swing that I can get out of this circuit here. That's what I want. Okay, so if I had to plot that maximum swing, then from the bottom, I might have 2 times an overdrive voltage. And from the top, right, from the top, now I've got 2 PMOS devices looking up that way. I've got to drop across this. The smallest voltage I could drop across that is going to be another 2 V overdrive voltages. Okay, so this point right here, the top floor of this is going to be determined by VDD minus these overdrive voltages. And so then I could say this is the best I can do with this. I could put a sinusoid here that's still linear between those two. Right? This will be V out min. This will be V out max. And you can see from my picture here, I'm starting to use up significant real estate here in terms of my swing, in terms of my power supply, right? Just with these 2 V overdrives there. So with a cascade, one of the nice things about these cascode type devices is they give you a lot of gain. But one thing you sacrifice is you're going to lose some swing. And what's more important, gain or dynamic range? Sometimes gain is more important. Sometimes dynamic range is, especially in communications, dynamic range is more important. Okay, but let's stick with this cascode here. So say we needed to get this kind of gain. We had no choice, but we need this gain. We're trying to get a very small signal. We have to gain that up as much as we can. So how can we design these V-bias generators to ensure that we have this maximum swing for this circuit? Okay, so let's make an attempt here. Let's try the simplest thing that we can do, and that's use an MOS cascode current source. And so what is that? Well, like I said, this is the simple way. And you can automatically think in your head, okay, if he's calling it simple, that means it must not be that good. And it's not going to be, and we'll show you why. So I want to generate voltages that will bias up these transistors M1 and M2 so that they're in the saturation region. And that's basically it. I want them to be in the saturation region, and I want them to have a very specific current. ID1 and ID2, which are equal in this circuit, which I'm going to call Iref. Right? So I'll have a VDD here. I'll have some current source here, which, as you've seen before, you can generate by just putting a voltage across a resistor. But I won't draw that just yet. But then once I generate this current here and I want to repeat that into this circuit on the right, one thing that I can do is just stack some transistors and do a replica type biasing like we've done in the past. Okay, so if I do this and I just diode connect these transistors, that, as we've seen before, automatically biases up those two transistors so that they are saturated, and so that they are saturated running a current Iref through them. Okay, so Iref runs through both of these. Let me call this M3 and M4. Okay, and so this is generating for me the V bias 1 and the V bias 2 that then go out and feed that cascode circuit that we've been playing with back here, this M1 and M2. Okay? So that generates an I naught, or an Iref, essentially, going through M1 and M2, and biases both of these things up. It's exactly what we want. Right? So what's wrong with this? Yes? Well, the problem is you can never have a floating terminal. You will have a floating terminal at that point, and that's something that it's going to be indeterminate. So you won't have that V bias, actually. You can, let's see, can you force? Yeah, you can't, because you don't know what that voltage is. That voltage can be large enough to even create a channel there. You don't know if it's larger than VT at that point, right? It's going to be something. It might be larger than, you might get lucky, be okay, but you don't want to take that chance. Okay, so you can diode connect these guys, and how good is this, right? This works, right? This looks pretty good. What's the problem? Okay, well, let's take a look at the problem here, right? You know the problem is going to be associated with swing, right? Because we just talked about dynamic range. We want this thing to have the maximum swing possible. That means we want this node here to be 2 VOVs, 2 overdrive voltages. Let's see if that's what it ends up being. Okay, so if I have this, I have a VGS here, and so that VGS is on. Remember, VGS, that's equal to VT plus an overdrive voltage, right? Because I can turn that around, right? That's from V overdrive is equal to VGS minus VT. But if VGS equals VT plus an overdrive voltage for a saturated MOS transistor, then I could say that across here I've got VT plus an overdrive voltage. Okay, if these transistors are identical, M3 and M4, which I'm assuming right here, which you usually have in a cascode type architecture here, then I can also say this is VT plus V overdrive. If they weren't identical, I'd have to assign them numbers, right? VT3, V overdrive 3, etc. Okay? And so if that's the case here, then at this node right here, after I've added all these voltages, that voltage plus that voltage, I have 2 times VT plus 2 times a V overdrive. Okay? And so now, if I have attached this node to this node of my actual amplifier here, then I'm going to have a drop here of VT plus a V overdrive, okay, which is going to say that that voltage right there is equal to what? It's VT plus V overdrive. I'm just summing different values of all of these things. Okay? And so that means I've dropped across this a VT plus V overdrive. And so when my output voltage, which is right up here, so when the output voltage of my PMOS transistor right here is going as small as it can go, how small can it go? All right. Well, this voltage is fixed here, right? This voltage is not moving. That's what it is, because this is all DC biasing here, right? It's a DC bias. That voltage is holding there. So that voltage is VT plus VOV, and so in the end, I can take this only down to VOV across M2, right? Because if M2 drops, if the drain to source voltage of M2 drops below VOV, it becomes triode, and my gain suddenly disappears. All right, and so that means that V output min is going to be equal to a VT plus 2 VOV. Okay, that is a problem, right? Because that's 1 VT higher than it has to be. Okay, so we don't like this at all. Okay? And you may say, what's the problem? It's just a VT, right? It's 0.7 volts. Yeah. Go on. I'm assuming that M2 and M4 all the way are equal right here. I'm assuming that M1, M2, M3, M4 are equal in this analysis right here. Okay, you'll see that they generally are, but even if they weren't, then I would have to put in, VT2, VOV2, right? But VTs are about the same amount, VOVs are about the same amount. Now, VTs are usually 0.7 volts, and if there's body effect, there'll be difference. We have to worry about that. But I'm just doing a simplified analysis. We're all the same. Okay, and in general, you'll see that they usually are. Okay, so if I were to use this to bias up this circuit to the right, I'm sort of shortchanging myself because I'm not getting this 2 VOV. I can't swing as far low as 2 VOV. I have to swing to VT plus 2 VOV. That's VT higher than I have to go. Now, how do I bias up this top portion? Well, if you're using a simple current source method, then to bias up the top portion, you may do something like this. And so that's why I was hesitating to do that. I mean, well, let's go ahead and write that in another color here. So you could do something like this, where you have some group of identical NMOS transistors. So you transfer this IREF current to here. That becomes IREF. And then up here, you're going up, and now you have a couple PMOS devices that are diode connected the same way. Okay, so I have diode connected PMOS devices, and these then become my V bias generators. And so this, for example, can be generating V bias 3. Okay, so I can still use these simple diode connected current sources to also bias up the top portion of this. All right? But if I do this, I'm really doing myself an enormous disservice. Because now, for this particular circuit, if I were to draw out its equivalent spectrum to this, or its equivalent output, where is that? To that. Let me just kind of steal that. Now what am I looking at? Now I'm no longer looking at something as simple as this. Okay, instead of this being V out max and V out min, now I got to add a VT to this. Okay, and so there's 2 V overages there plus a VT. So maybe that's what that is there. That becomes VDD minus 2 V overages minus a VT. This now becomes VT plus 2 VOVs. Now my output swing becomes minuscule. Right? This now becomes my V output max. That becomes my V output min, and my dynamic range just disappears, right? I'm looking at a signal, maximum signal, it can only be this big now, right? That's very bad. So the problem here is the dynamic range shrinks in a big way when I'm using these cascodes versus not using the cascodes. All right, or simply having this simple current source or simple cascode current source. Okay, so how bad is this problem? Let's put some numbers in this. Okay, so my V output min is Vt plus 2 overdrive voltages. What's a typical value for Vt? So that's 0.7, and that's probably what it's going to be for at least this bottom transistor, because it's not, doesn't have a source. The source is tied to the bulk. Right, for this top transistor, it's actually going to be a little larger than that, right? And so I'm sort of taking the best case right here. So that's going to be about 0.7. What's a typical value for the overdrive voltage? Those are safe values, right? But bipolar is like 0.2, right? MOS, maybe it's 0.3 or so you're dropping across that. Depends on the device too, right? You can control that to whatever you want. But say it's 0.3 in this case. That means I got 1.3 volts as V output min, right? And this is a lot. In a 2-volt supply, right? So if you had a 2-volt supply, this is taking away more than half of your voltage there. Right? Let's call it a 2-volt supply technology. Okay, and you know, it's if you had a smaller voltage, this is just simply not permissible in a, say, 1.1. Say VDD is 1.1 volt technology, which is where a lot of analog circuits are now, right? They're at 1.1 volts. They're dropping even below that. Okay, in the most aggressive type technologies, that's where a lot of them are at this point, at least in research. Okay, so how do we solve this problem? This is obviously a problem, right? Because if we have a 2-volt supply, this is not even going to work at all. Instead of showing this amount of headroom, right, I'd have negative headroom, right? Because I would have to have 1.3 volts from the bottom, 1.3 volts from the top. I've got no headroom, negative headroom. Okay, how do I solve this? We'll have to play some tricks. And so that's why we need to talk about now a high swing cascode. Let's talk about the solution to this. And that's a high swing cascode, and this is really a V-bias generator. It's the way that we want to generate our V-bias voltages, such that our cascode circuit can swing very wide. Okay, so how do we do this? Well, the basic idea is to level shift. So you level shift the voltage down to move the VG2 of M2 to get something smaller. So here's M2, this device. We're talking about this device, the one that's stacked on top of M1 in the cascode. And I'm running out of space there, so let me just draw it here. So there's M1, there's M2. If we can get VG2, which is the voltage on the gate of M2, to be equal to VT plus 2 VOV. If we can do that, and then I drop across this a VT plus a VOV, then this node here will be VOV. Okay? And this device here will have across it VOV, and that device here can have across it VOV, which means that my V output minimum returns to 2 VOV. And that's what we want. Okay? So the trick is to change this circuit that we have before. So here's the circuit before, right? This was too simple here because if I put 2 diode connected transistors right there, then that voltage here becomes 2 VT times 2 VOV. Right? That's 1 VT more than I need. And so if I could somehow create a bias voltage at this node that's equal to VT plus 2 VOV, then I've got my maximum swing out of this cascode. Okay, and it all takes a level shift here. It all takes a circuit that looks like this. So I'm going to start out with that circuit that I've already complained about, right? Because there may not be a better way to do this here, which means bias up these transistors such that they take on the voltages corresponding to the currents that are going through them. So I'm going to keep the diode connections of these things, because diode connections shove a current through a diode connected transistor, it automatically biases that thing up. Right? That's definitely one thing that we want. But now what I'm going to do is I'm going to stick in a level shift right across there before I go into this device, M2. And that's all I'm going to add to this thing. That single level shift. I still want my output current to be equal to my reference current IREF. Okay, but now if we look at this thing, we can do that exact same analysis. Right across here we have VT plus VOV. Here we have another VT plus VOV. That does still generate 2 times VT plus VOV here, but now we're going to level shift that down by VT. We're going to have, and if we level shift down by VT, that becomes VT plus 2 VOV. I missed the 2 on this one too. This transistor itself will have its own level shift, VT plus VOV, and we'll end up right here with the VOV that we want. Okay, so if we're able to create this kind of circuit where we have that level shift, then we've got what we want. All right, so can we create that level shift in an easy manner? Well, let's take a look at that. So usually, what do we have to use to create that level shift, right? We've got a transistor. Okay, so maybe the best way to do that level shift is to stick in a transistor there. But we're going to see very quickly that there's going to be a problem with this. And that it's not easy to get a VT level shift. Okay, so let's take a look at one way we might be able to do this. And so perhaps we're just going to take a single transistor like this. We're going to bias it up with some current source, like that. Okay, and this will be its input. And this will be its output. So the output should be level shifted from the input, and we want that level shift to be VT. Right? But we know that if this is a saturated transistor, then this voltage is going to be VT plus VOV. It's not equal to a VT. All right? And we want just a VT level shift. Okay? So how can we get that VT level shift out of this transistor? Well, we can look at the equation for the overdrive voltage. Remember what that equation is. That's square root of 2ID divided by, it's an MOS device, so mu n C aux times the W over L ratio for that. That's what the overdrive voltage is. And if we could make that overdrive voltage go to 0, then we got a VT level shift. Okay? So how do we make that overdrive voltage go to 0? Well, basically, we're going to need to take this W and push it up. Okay? If we make W go up, the overdrive goes down and eventually gets close to 0. Okay? So we can use a large device and small current. And that gives you your VT level shift. Okay? You like that solution? If not, what do you not like about it? The large device, right? No one wants a large device somewhere on this. Okay, so not the best solution. Due to the need for a large device. Okay, always best to avoid large devices. Okay, so it's not easy to get just a VT level shift without having to use a big device. But it is easy to get a VT plus VOV. All right? And so want to avoid this large device. And so in order to do that, let's still use this kind of topology here. But let's now just accept that across this device we're going to level shift VT plus VOV. So other option, just accept a VT plus VOV level shift. And try to change something else in the circuit. Okay, so I'm still going to use this guy here. It's still going to have some current source under it. And it's still going to be the interface device before I get to my M1 and M2 here. It'll still be feeding M2. It'll still be doing the level shift, but now its level shift is going to be a VT plus VOV. And somehow, I'm going to need to create at this node here 2 VT plus 3 VOV. Because if I'm able to create 2 VT plus 3 OV here, and this is where my work is going to have to be, I need this, then at this node I'll suddenly have a VT plus 2 VOV, and when that gets level shifted VT plus VOV, I end up with the VOV that I want. Okay? This seems like it's going to be a little more complicated, but it's actually not that hard to do. Okay, and it has to do with how we design this side here. Let's redraw the whole thing here rather than design it from there. Okay, so Thus, I'm going to end up with the following circuit. Where on this side, I'm still going to do my simple current source thing. I have some reference current here. I'm going to push that reference current into two diodes, or two diode-connected MOS devices. So I'll call M3, M4. And I'm going to have that level shifting thing pulling straight up to VDD from the drain, pulling down into another device that's really serving as a current source now for it. So I've sort of implemented this little current source that I've drawn right there using an MOS transistor. Call this M5, call this M6. And then this goes on to bias up the actual current source used in my amplifier. So here's M1. Let's pull this back a bit. And then M2. And there's my eventual I0, which I want equal to my reference current Iref. Okay, so this now becomes a circuit that I've made, and you can see I've pretty much drawn what I have up here, except now I filled in the details as to how I'm generating the currents on this side with M4. And so again, I have a couple goals here. One of my goals is that at this node here, because it's before the level shift, I want 2 VT plus 3 VOV. Because if I have that, then this becomes VT plus 2 OV, and then this becomes VOV, which is what I want, what I ultimately want. So how do I get this 2 VT plus 3 VOV around that device M4? That becomes our big question. How would you do it? So right now, if I had to really look at this, let me use green on this. What do I have? Across this, across M3, I have a VT plus VOV. Okay? And in order to get 2 VT plus 3 OV right here, I have to drop across M4. Did I say M4 before or M3? I mean, across M3 I have VT plus VOV. Okay, but then across M4, in order to get this 2 VT plus 3 VOV, I have to have a VT plus a 2 VOV. Okay, so I need this. Okay? And so if I need this, how am I going to get that? I'm going to get that by just resizing my devices. This is, okay, good. So to get this, I have to size M4 accordingly. Okay, and how do I determine what M4 has to be? Well, I have to think about the currents going through these devices. So these currents, right, they're stacked, so they have the same currents going through them. Right, but I can write expressions for their drain currents. So I can write an expression for ID3, of course, that's 1/2 mu n C aux times a W over L of 3 times an overdrive of 3. Squared, right? Because VGS minus VT is what we've called an overdrive voltage. Okay? I can also write a similar equation for device 4. So ID4 is going to be 1/2 mu n times Cx times W over L4 times the overdrive of 4. But I want the overdrive of 4 to be 2 times an overdrive of 3. Okay? So this here is just my different way of writing the fact that I need this. right? And in this way, if the overdrive of 4 equals twice the overdrive of 3, I've got effectively a 2 VOV across this device plus its VT. Okay, so how do I do this? Well, I just recognize one thing, that ID3 is equal to ID4. That's equal to my IREF voltage, right? So I can equate these two things. I could say ID3, 1/2 mu n Cox W over L3 times an overdrive of 3 squared is equal to 1/2 mu n Cox W over L4 times 2 times an overdrive of 3 squared. And you can see right away, obviously a lot of things cancel out. All of these things cancel out here, and I'm left with these two here. All right, even these overdrives cancel out, so that cancels with this here, and that becomes a 4 because it's squared by the square factor right here. And so finally, this really simplifies down to just W over L. Let's do it in green. W over L4 just has to be 1/4 the size of W over L3. If I satisfy this, then I'm going to get 2 VOVs across M4. Okay, this thing here, the best way to do this. This thing here gives me that. Yes? Cox and VT. No, Cox is a capacitance per unit area, right? So it's not the actual capacitance. It's just right in the mu n Cox. So the VT we'll have to talk about in a second, right? Because we'll have some VT issues here that we'll have to look at. But if there were no VT issues, this would be the equation you would use, 1/4. But in actuality, we're not going to be able to do 1/4 because of the VT issues you're mentioning. Basically, a transistor will end up not in saturation if we do this. But let's get to that point. Yes? Oh, yeah. That's a good idea. What time is it? Okay, so this is homework number 2. This is homework number 1. So let's start these passing around. Let's start them both on this side here. Yeah, just grab your homework 1 and your homework 2 and then pass them down. Actually, that's stupid, isn't it? I should. Yeah, I'll go to the other side here. Okay, and so in this derivation, right, I'm assuming that M3 is our unit device, right? So we sort of define V overage, the overdrive voltage for M3 as the unit overdrive voltage, right? So M4, we're having 2 times that unit. So to finish this picture, right, all these V overdrives have to be equal to the overdrive of M3. So I want to make all these other devices, since they all have the same current going through them, all the other devices have to be the same as M3. So I can add to this and W over L of 1 we want equal to W over L2, of course equal to W over L3. We know what W over L4 is, equal to W over L5, equal to W over L6. Okay? And so that's the design strategy that will put this V overdrive at the drain of M1, and that will give you the maximum output swing. V out min equals 2 V overdrives. Okay? But, it's been mentioned already, there's a problem with this. So let's talk about that problem. And that has to do with the body effect. In M4, M5, and M2. Okay? And so what does body effect do to you? It changes your VTs. Right? So it'll increase their VTs. So let me grab this circuit again here. If you're trying to take notes, don't worry, because I have to clean it up too. And as you've seen, that takes me some time. But I'm just lazy and don't want to redraw that circuit. Actually, I don't have to clean it up too much. Those are all still good things on it. I at least want to clean this up, though. So if I looked at this circuit in more detail here, how it's really hooked up, right? All of these devices on the bottom here, this M3, M6, and M1, essentially I've tied their sources to the bulk, right? Because for NMOS devices, usually you're tying the bulk to ground, so I could say that their bulks are basically tied to ground. These devices right there. But those devices up top, not true. So that's why I'm saying the last thing that I said here was that I have to worry about M4, M5, and M2 because their threshold voltages are not just 0.7 volts. They're not just the VT naught. They're VT naught plus some amount due to the body effect. Okay, so I have to be careful about that. What did I do here? And so how do I address this sort of thing? Well, I already know that I've designed these things up here as this being, if this is a W over L, then this is 1/4 of a W over L right here. And what I've essentially done, yes?
Is that line going from M6's, I guess,
Oh, yeah, you're right. That's actually, yeah, you're right. That's the gate line. So I have to be clear about, yeah, this is a different line. So I have to do that. Okay? That's the bulk. Okay, so what do we know about this circuit now? So if we take into account that we have different VTs for each of these devices, right? So I could say this device here is going to have across here a VT3 plus a VOV. This device is going to have its VT4 plus 2 VOVs if I've designed it to be 1/4 of the size of all the other devices there. Okay, so what that's going to put at top here is this voltage being equal to VT3 plus VT4 plus essentially 3 overdrive voltages for these devices. Okay, where now I'm taking into account that my VTs are not necessarily all equal, so I have to take into account, so I'm putting their subscripts there for all of these. Okay, so if all these devices as well, these are all W over L's then, in the design that we've done here. That means that I'm going to get a level shift across M5, which is going to say that the voltage at the source of M5 is going to be VT3 plus VT4 plus this 3 overdrive voltages minus now VT of 5 plus an overdrive voltage there. Okay? And so finally, what I'm going to have at this node right here is going to be a VT3 plus VT4 minus VT5. It's going to be minus a VT of 2. And then finally plus 1 overdrive voltage. Okay? Now, for M1 to be in saturation, this voltage better be greater than 1 overdrive voltage. All right? So what we really need to do is take all of this stuff and determine whether that addition and subtraction of different VTs is going to be greater than 1 or less than 1. Because if it's less than 1 and it's added to this VOV, then this whole thing is going to be less than a VOV. Okay, so let's start looking at this in a little bit of detail here. So, first of all, I know that Vt of 4 is not going to be equal to Vt of 5. 5 of M5 here is just going to be equal to a Vt, approximately a Vt of 2 plus 2 times the overdrive voltage here. Okay, and so which is the bigger voltage that we're looking at here? Obviously, 5 has the bigger voltage, right? So it's got a larger bulk to source voltage that we're looking at, which means that the threshold voltage of 5 is greater than the threshold voltage of 4. Okay, so if the threshold voltage of 5 is greater than 4, you notice that I have a Vt4 minus Vt5 right here. That means this thing right here, that's negative. So that's subtracting from this whole thing. And, you know, that if this thing here, Vt3 minus Vt2 were 0, then I'd have this voltage would be less than an overdrive voltage, and M1 would not be saturated. Okay? And so let's find out about this Vt3 and Vt2. So obviously Vt3 is not going to be equal to Vt2 because, again, Vt3 has no source to bulk voltage. And so obviously Vt2 is going to be greater than Vt3. And so if that's the case, then I can take a look at this part of that equation, and that is also going to be negative. So I got VOV minus a small amount minus another small amount. This, of course, is going to be less than VOV. And if that's less than VOV, that's the voltage that's dropped across M1, right? If that's less than VOV, then M1 is not saturated. Okay? M1 is not saturated. You no longer have a high impedance current source. Or at least the current source impedance is not as high as you expected it to be. Your gain is going to be very small. This obviously is a bad thing. Okay, so we need to do something about this. So it all worked out nicely in our little calculation where we ended up saying, oh, we need WL4 to be 1/4 W over L3, but to this. Okay, so what's the simplest solution you can think of if all it took was changing this picture right here? What's the simplest thing you can do to solve this problem? You don't care about technology or anything. Simplest thing you can do is just get rid from these transistors M4, M5, and M2 to their sources. So that's solution number 1. So tie the bulks, actually I should say the wells. The bulk is a well, but for a PMOS device, for example, that's in an N well, you would need to tie the wells. So tie the wells of, what are they, M4, M5, and M2 to their sources. And what this does is eliminate body effect. So all VTs the same. And we have no problem in the end. Okay? Why do we not want to do this? It's not practical, right? If we had to give each of these devices their own well, they would take up more space than they should. And we don't like that. We especially don't want that to happen to M2, right? Because M2 is like the current source of an amplifier device, right? All of this stuff we wouldn't mind from M3 through M6. We wouldn't mind too much because there's only one of those, right? That one will then direct these V-bias voltages to all the different amplifiers out there. But we certainly do not want to do it to M2, right? Because that means we'd have to duplicate those transistors with their own wells, and that takes space. Okay, so this is not practical. It takes up area to give each device its own well. Okay? And so, what else can we do about this? What's another solution? Solution number 2 is just use a biasing strategy. So just bias M4 so that we do have a situation where VOV, at least VOV, is dropped across M1. So bias M4. So that, say, the VGS4 is going to be greater now, not just equal to, but greater than VT plus 2 VOVs. So in other words, VGS4 has to be equal to a VT plus 3 VOVs. Okay? And so now, what does that mean? In order to do that, that means you want to make M4 even smaller than 1/4 of W over L of device 3. Okay? And if I wanted to do this, say I wanted to make it just this voltage right here, then you can do that exact analysis that we did, and you'll find that what you need is that W over L4 has to be 1/9 W over L1. Okay, that would do the job for you, but basically all you're doing, whereas device 1, because of the strategy that we're trying to do to give us maximum output swing, has just one VOV across it. All right, so VDS1, our issue is that VDS1 does not equal VDS3, and if that's the case, then that automatically that means that I0 is now no longer just equal to IREF. It's equal to a ratio involving the drain source voltages of M1 and M3 times IREF. So it's equal then to this, 1 plus lambda times VDS of 1 divided by 1 plus lambda times VDS of 3 all times IREF. And so I0 is not equal to IREF. Okay? Some people don't like this. In some ways, it may not matter that much if your lambda is very small, right? Usually lambda is very small. And that's the case for, 0.25 micron type processes or something, even 0.18 or so. But when you start dropping down to 64 nanometer, 34 nanometer, etc., now this lambda is no longer as small as you'd like it to be. And you may get significant differences in currents here. And so we need a solution against this. And that solution is just to use an alternate biasing scheme for this. We'll talk about that next time. Okay? So I will see you next Tuesday.